Hi, welcome to the screencast for the second part of Chapter 6, or what I'll call 6.1b from the Brown SL chemistry book. So we talked about the rates of reaction, and now we're going to talk about how do you actually measure these rates. Since they have to be done experimentally, the graph has to come from somewhere, so someone has to do the experiment to get the data to make those graphs. So what you have to do is decide if you're going to measure the change in the reactants or the products, and it really depends on which is easier to observe. You usually don't measure the concentration directly because that means you'd have to take a sample out to titrate it or in some way determine its concentration. So instead, we use some kind of signal that's related to the change in concentration, like the volume of gas being produced or the amount of mass of the reactant being consumed as the gas escapes, or a change in color, change in pH. All those things can be used to indicate the change in concentration. So there's really 6 common techniques or signals that are used, and really 4 of them are the preferred ones, and we'll talk about why. But for each of them, you have to control the temperature throughout the reaction because temperature has a huge effect on reaction rate. And usually temperature is controlled by doing the reaction in a water bath. So you have your beaker or your test tube or whatever immersed in a water bath, kept at a constant temperature. So common techniques used to determine the rate of reaction are change in volume of gas produced, change in mass, that's of your reactants typically, although it could go up or down, change in the transmission of light, so there's a color change with your reactant and product, change in concentration measured by titration, so there's a pH change in concentration measured by conductivity, so there's a change in ions, or something called a non-continuous method or a clock reaction where you look for a certain point to be reached. So let's look at technique 1, change in volume of gas produced. This works really well if a gas is being produced because it allows for what we call continuous readings. That means over the entire time span of the reaction rate, you can be taking readings. You can take them every single second if you want, or if you have some kind of probeware, the probeware can continuously monitor and record what's happening, and you get really good graphs from this. So the gas can be collected with the gas syringe attached to the flask. So the gas goes up and it pushes the plunger out as it collects. That's one way to do it. Or you can also collect it by water displacement, which is the second one in my little picture down there, where you fill up a burette or graduated cylinder, some kind of container with marks on it. You fill it with water and flip it over into a water bath, and then you let the gas run through a hose from your test tube or whatever your reaction vessel is over to the collection container. So water displacement works well if your gas isn't highly soluble in water. So if it is highly soluble, then the gas syringe is a better method to go with. The gas syringe, you have to be a little bit careful though, because there's not as much space there, and you can have other issues with that. So we typically would use water displacement. And as far as the solubility, if you use warm water, it would help decrease the solubility of the gas. Either way, if you're looking at the change in volume of gas produced, because you're measuring a product being produced, your slope of your graph will be positive. The second technique is to look at the change in mass. And generally what this means is that instead of collecting the gas being produced, you're letting the gas escape. And then that means there'll be a decrease in mass. So you can put your reaction vessel on the balance, and instead of having a syringe or water displacement hooked up to it, you just let the gas go. And this also is a good technique because it also allows for continuous readings over time. And again, if you have probeware hooked up, you can get many readings, every minute and get a really good graph from this. And this works well for denser gases such as CO2. It doesn't work so well for light gases like hydrogen or helium, although helium wouldn't be involved in a reaction typically, but it won't work well for those light gases because the change in mass might be too small for your balance to detect. So depending on how good your balance is, this may or may not be an appropriate method. In this case, the slope of the graph is going to be negative because you're really measuring the change in the concentration of the reactant. Third technique depends on there being a color change between your reactant and product. And you can do it by using a colorimeter or a spectrophotometer, which measures the amount of a specific color of light that is being absorbed by either the reactant or the product. Whichever one has the color is the one that's absorbing that certain frequency. So it works well, obviously, if one is colored and the other one is not, or if an indicator can be used to color one of the reactants or products. So your color will either deepen or lighten over time. If the color deepens, then the amount of light absorbed increases and less light is going to be transmitted. If the color lightens, then the absorption decreases and the amount of light transmitted increases. So this is also a good technique as it allows for continuous readings over time. And the slope of the graph is going to depend on whether your color is getting lighter or darker. So how do you know if there's going to be a color change? Well, the most common reason is because you have a transition metal that is changing its oxidation state. It's going from a +2 to a +3 or +1 to a +4. So how would you know that? Well, cobalt and manganese are going to be the two common ones. If you see those involved, then quite likely color change will be occurring. But any transition metal could be involved in a color change. Technique 4, change in concentration measured using titration. This means that either your reactant or product changes pH. H plus is being produced, H plus is being consumed, OH minus is being produced, or OH minus is being consumed. But this is a pain because you have to remove a sample from the reaction vessel for every data point you want. So this is not a continuous reaction. And the other thing is when you take it out of your reaction vessel, it's not like you can just take out the reactant or the product. It's all occurring in there. So the reaction is going to go on while you're trying to measure the concentration of the reactant or product, or as you're trying to measure the pH. So oftentimes they use a technique called quenching, which like freezes or stops the reaction. But it's a messy reaction to do. You have to take a sample out every time you want a data point and then quench it and measure that concentration. So this would be a last resort to use if the first three techniques or the next technique isn't available. Then you might think about using titration. Change of concentration measured with conductivity. This is far easier than looking at pH because the conductivity depends on the total number of ions. So if this changes during a reaction, conductivity can be used to find the reaction rate. And again, you can measure it continuously over time with a conductivity meter. If the products contain more ions, then the conductivity should increase. It'll be a positive slope. But if the products have fewer ions or the reactants contain more ions, then the conductivity will decrease and we'll see a negative slope. Either way, it will give us a good idea of what's happening to the reaction rate. And then the last one is called a non-continuous method. That's because you only get one reading. Okay, a continuous method means you keep getting a data as frequently as you can take it. But a non-continuous means you're waiting for one point to be reached. You're looking for what we call an endpoint. So if it's difficult to use one of the other 5 techniques, then you might just look for something observable that can serve as, boom, the reaction is done here. And then it gives you an average reaction time from when it started to when it ended. But it doesn't tell you anything about the rate over that time. So we're not going to see any change in slope. We're just going to have an average reaction rate. But it can be used if need be. For example, if you want to watch for the complete time for magnesium ribbon to completely disappear in HCl, or if you're watching for enough time for precipitate to form in a beaker and you put like a cross on the bottom, and when that's all covered up, you're like, boom, that's it, that's the end point. Or time for all the color to leave the containers viewed against a white background. So times you might use this is if you're changing a variable and you want to see if it affects the reaction time. You maybe don't need to have continuous data. You just want to know, did it make the reaction faster or slower? So you can watch for this endpoint to be reached and see if it took more or less time.